Imagine a universe where every decision you make creates a new reality, where particles spontaneously pop into existence from nothing and time itself flows backwards. In this universe, you chose to watch this video, but in another, you scrolled past. Our perception of reality is shaped by classical physics, where objects have definite positions and predictable trajectories. But beneath this familiar world lies the realm of quantum physics, and it's about to change how you see everything. As we enter into the quantum realm, reality becomes even stranger than time paradoxes and multiverses. Objects can exist in multiple places simultaneously, and the very act of looking at something fundamentally changes its nature. This is the fundamental principle of quantum mechanics known as superposition. It challenges our most basic assumptions about reality and forces us to reconsider everything we thought we knew about the nature of existence. Picture a beam of particles, such as photons, fired at a screen with two parallel openings, or slits. Classical physics predicts that these particles would create two distinct bands on the screen behind the slits. However, the actual result is far more puzzling. When the particles pass through the slits, they create an interference pattern on the screen, similar to what we'd expect if we were dealing with waves rather than particles. This observation suggests that each particle somehow passes through both slits simultaneously, interfering with itself like a wave would. But here's where it gets truly mind-bending. If we attempt to observe which slit each particle passes through, the interference pattern disappears, and we see two distinct bands as originally expected. Just by observing, it seems like we force the particles to act like regular objects, picking one path instead of behaving like waves. It's as if reality itself is uncertain, existing as a cloud of probabilities until we interact with it. But if particles can exist in multiple states simultaneously, what does this mean for the objects they compose? Is the chair you're sitting on truly in one definite location, or is it in a superposition of many possible states until observed? These questions lead us to one of the most debated interpretations of quantum mechanics, the Copenhagen interpretation, which suggests that quantum systems exist in a superposition of all possible states until a measurement collapses this superposition into a definite state. In other words, reality as we know it may not exist in a concrete form until we observe it. Yet, the strangeness of quantum mechanics doesn't end with superposition and uncertainty. What if two particles could remain connected regardless of the distance between them, instantaneously influencing each other's states? This is quantum entanglement, or what Einstein famously called spooky action at a distance. In a typical entanglement scenario, two particles become inextricably linked, sharing a quantum state that persists even when they're separated by vast distances. If one particle's spin is measured and found to be up, the other particle's spin, even if it's light years away, will instantaneously be found to be down. This correlation occurs despite the absence of any direct interaction between the particles, which violates the principle that information cannot travel faster than light. Either information is somehow transmitted instantaneously between entangled particles, or locality, the idea that objects are only influenced by their immediate surroundings, breaks down at the quantum level. Physicist John Bell developed a theorem that allows for experimental tests of entanglement, demonstrating that the predictions of quantum mechanics cannot be explained by local hidden variables. Recent experiments have confirmed Bell's theorem, showing that entangled particles behave in ways that defy classical intuition. These findings reinforce the idea that measurement affects the state of quantum systems in ways that challenge our understanding of cause and effect. Quantum entanglement also holds promise for the development of a quantum internet, where pairs of entangled photons could transmit information securely over vast distances. But the implications of entanglement extend far beyond practical applications. It challenges our very notion of reality itself. Physicist Holger Hoffman's research suggests that an object's reality is deeply connected to everything it interacts with. You can't separate the object from its surroundings in the way it interacts with them. This challenges the idea of a completely objective reality, showing that the way particles are connected at the quantum level has major implications for how we understand space, time, and the nature of existence. In quantum mechanics, measuring a particle doesn't just reveal its state. It suggests that what different observers perceive as reality might not be the same. This challenges our classical intuitions, pointing to a universe that is more interconnected and observer-dependent than we ever imagined. While entanglement reveals the interconnectedness of particles, another quantum phenomenon questions the nature of existence itself. What if particles could spontaneously pop into being from seemingly nothing? The Schwinger effect proposes just that, forcing us to reconsider our understanding of vacuum and the origins of matter. In quantum mechanics, the concept of vacuum is fundamentally different from our classical understanding. It's not an empty void, but a state with the lowest possible energy filled with fluctuating quantum fields. These fields spread through what we perceive as empty space, giving rise to virtual particles that pop in and out of existence. The Schwinger effect takes this concept a step further. It demonstrates that under certain conditions, particles can spontaneously materialize from a vacuum. This effect suggests that even empty space is not truly empty, but filled with potential energy and matter. In a strong enough electromagnetic field, particle-antiparticle pairs can be created from the vacuum without any initial particles present, which means that something can come from nothing. This means that the universe can create matter from seemingly nothing, fundamentally changing our view of material reality and the origins of matter. Recently, researchers demonstrated the spontaneous creation of particle-antiparticle pairs in a laboratory setting using graphene. Additionally, the Casimir effect shows how even in empty space, tiny energy fluctuations can create a force that we can actually measure. This effect shows that when two uncharged metallic plates are placed close together in a vacuum, they're pulled toward each other. This happens because of tiny energy fluctuations in the electromagnetic field, proving that even empty space isn't really empty in the quantum world. This gives us the possibility that our everyday understanding of reality is purely a convenient approximation. The Schwinger effect aligns with the broader implications of quantum mechanics, suggesting that our understanding of the universe is far more complex than previously assumed. It indicates that the universe itself might be fundamentally uncertain, with the potential for matter to spring into existence at any moment. This phenomenon raises intriguing questions about the nature of the universe and its origins. If particles can spontaneously appear from a vacuum, could this process have played a role in the early moments of the Big Bang? Could it explain the apparent imbalance between matter and antimatter in our universe? Moreover, in classical physics, we learn that matter and energy cannot be created or destroyed, only transformed. But in the quantum realm, it seems that these rules can be bent, if only for fleeting moments. The Schwinger effect hints at a universe far stranger than we imagined, but it's just the beginning. What if your existence isn't limited to just one reality? Quantum mechanics suggests a multiverse where every possible outcome of your choices becomes real. In this framework, the concept of death takes on an entirely new meaning. Rooted in the many worlds interpretation of quantum mechanics, quantum immortality proposes that every decision point in our lives creates a branching universe, each representing a different outcome. In this infinite multiverse, every possible version of you exists simultaneously. When faced with a life-threatening situation, the theory suggests that your consciousness will always follow the path where you survive. From your perspective, you would never experience death, as your awareness would continually shift to realities where you continue to live. Imagine you're playing a game of quantum Russian roulette. In this scenario, a quantum measurement determines whether the gun fires. According to quantum immortality, you would always experience the outcome where the gun doesn't fire. In parallel universes, other versions of you might not be so fortunate, but your conscious experience would never encounter those realities. Moreover, quantum immortality intersects with the philosophical debate between Einstein and Bohr on the nature of reality. Einstein famously rejected the probabilistic nature of quantum mechanics, stating that God does not play dice with the universe. Bohr, on the other hand, embraced the inherent uncertainty in quantum systems. The theory also raises intriguing questions about the relationship between consciousness and quantum mechanics. If our conscious experience can navigate through multiple realities, does this imply a deeper connection between awareness and the fabric of the universe? Some researchers propose that consciousness itself might be a quantum phenomenon, potentially explaining its elusive nature and our inability to fully grasp it through classical models of the brain. However, it relies on interpretations of quantum mechanics that, while mathematically consistent, are far from universally accepted in the scientific community. Critics argue that quantum immortality suffers from the anthropic principle, the idea that we observe a universe compatible with our existence simply because we wouldn't be here to observe it otherwise. They argue that the theory doesn't necessarily imply subjective immortality, but rather an infinite number of finite-lived versions of ourselves across the multiverse. But quantum immortality is just the tip of the iceberg. What if the very foundation of cause and effect, the bedrock of our understanding of reality, is fundamentally flawed? Recent experiments in quantum mechanics suggest that the future might influence the past. In the realm of quantum physics, time doesn't always flow in the direction we expect. Suppose we take the double slit experiment from before, but this time we add detectors at the slits to determine which path each particle takes. Classically, we'd expect that by observing particles, it would choose one specific path, which in turn would eliminate the wave-like pattern that usually forms when they are not observed. But that isn't the case. If you add a device that erases the information about which path the particles took, even after they've already passed through the slits, the wave-like pattern reappears. This seems to suggest that a future choice can somehow affect a past event. Taking this concept even further, if the decision to erase the path information is made after the particles have passed through the slits and been detected, this future choice still affects the interference or wave pattern created in the past. If future choices can influence past events, does this mean our decisions are predetermined? Or does it suggest a more complex, interconnected view of time where past, present, and future coexist in a way we can't fully comprehend? Some physicists propose that these paradoxes point to a block universe model, where all moments in time exist simultaneously, and our perception of time's flow is merely an illusion. Others suggest that quantum mechanics might require a new understanding of causality altogether, one that allows for retrocausality, the idea that effects can precede their causes. Moreover, these time paradoxes intersect with other quantum phenomena we've discussed. Could the apparent paradoxes of quantum time be explained by interactions between parallel universes? Some theorists suggest that information might be able to travel sideways in time, between parallel realities, rather than strictly forward or backward. Or the observer effect, for instance, when we consider that the act of observation might not just affect the present state of a particle, but potentially its past and future states as well. This leads us to an even more startling possibility. What if our consciousness doesn't just passively perceive the world, but actually plays a role in shaping it? Could objective reality be an illusion? with each of us participating in the creation of our own subjective universe? Consider the thought experiment known as Wigner's friend. Suppose an observer watches another observer perform a quantum measurement. According to quantum mechanics, the friend's measurement should collapse the quantum state or force the system to settle into one specific outcome out of all the possible outcomes. However, from Wigner's perspective, the entire system, including his friend, should remain in a superposition until he makes his own observation. This paradox suggests that different observers might experience different realities based on their measurements. It challenges the notion of a single reality and implies that facts themselves might be dependent on the observer. The relational interpretation of quantum mechanics takes this idea further, proposing that the properties of quantum objects are not intrinsic, but depend on their interactions with other systems, including observers. These ideas challenge our conventional understanding of the brain as a purely classical system. If quantum effects play a role in consciousness, it could explain some of its more mysterious properties, such as the subjective nature of experience or the apparent unity of conscious awareness. It might also provide a mechanism for phenomena like intuition or creativity, which seem to arise from processes beyond our conscious control. Some researchers argue that these phenomena point to a deeper connection between consciousness and the fabric of the universe. Such ideas have led to some even more radical theories. For instance, the quantum mind hypothesis suggests that consciousness might be a fundamental property of the universe, just as important as space and time. In this view, our individual consciousnesses could be seen as a small part of a larger, universal consciousness, similar to how particles are part of bigger energy fields. This connects with another concept known as the observer effect, which suggests that we're not passive spectators in an objective universe, but active participants in a reality that responds to our attention. This view aligns with ancient philosophies that see consciousness as a fundamental part of the universe, rather than the result of complex neural activity. Beyond shaping our observations, quantum effects could be driving the most basic processes of life, from the efficiency of photosynthesis to the unnatural precision of bird migration. Research indicates that during photosynthesis, energy packets called excitons use quantum superposition to explore several different paths at once. This makes sure that the excitons reach their destination, the reaction center, with remarkable efficiency. The quantum nature of this process allows plants to harness light energy far more effectively than classical physics would predict. Further, consider the European robin, a bird capable of navigating vast distances with astonishing precision. Scientists have discovered that these birds likely use quantum entanglement to sense the Earth's magnetic field. This allows them to orient themselves during long migrations. Even our sense of smell might rely on quantum phenomena. Traditional theories suggest that olfaction is based on the shape of odor molecules. However, recent research proposes that quantum vibrations, rather than just molecular shape, play a crucial role in how we detect and differentiate smells, which could explain the exquisite sensitivity and specificity of our noses. The efficiency of enzymes, the catalysts that drive countless biochemical reactions in our bodies, may also be enhanced by quantum effects. Some researchers suggest that quantum tunneling allows enzymes to accelerate reactions significantly faster than classical processes would permit. This quantum boost could be essential for maintaining the rapid and precise biochemical processes necessary for life, raising the question of whether quantum phenomena are the missing link in how life emerged from non-living matter. Moreover, the discovery of quantum effects in biology challenges our understanding of evolution. If quantum processes play a fundamental role in life, how has natural selection shaped these quantum-level adaptations? This question opens up new avenues for research and could potentially redefine our concept of fitness in evolutionary theory. Understanding how nature harnesses quantum effects could lead to revolutionary technologies. Quantum-inspired solar cells could dramatically improve energy efficiency, while quantum-based sensors could transform medical diagnostics and environmental monitoring. But theoretical physics offers an even more radical view about the nature of our reality. The holographic principle, a concept that emerged from the study of black holes, suggests that our three-dimensional universe might be encoded on a two-dimensional surface, much like a hologram. According to this theory, all the information that falls into a black hole is not lost, but rather encoded on its event horizon. This concept suggests that the information contained within black holes is preserved and can be reconstructed, resolving the long-standing black hole information paradox. Additionally, it suggests a deep connection between quantum mechanics and the very fabric of space-time. This connection indicates that the universe may be fundamentally constructed from information, challenging our traditional notions of space and time. In a holographic universe, these seemingly spooky connections of quantum entanglement might be explained by the underlying two-dimensional information structure. It suggests that the laws governing subatomic particles and those governing vast cosmic structures might be more unified than previously thought. This could potentially lead to a long-sought theory of everything that combines quantum mechanics with general relativity. The holographic universe model also assumes that particles and their interactions are not independent, but are instead part of a collective reality shaped by entanglement. As physicist Sean Carroll suggests, quantum theory indicates that the world we experience is only a higher-level emergent description of a more fundamental quantum reality. The holographic principle takes this idea further, proposing that even this quantum reality might be an emergent property of an even more fundamental information structure. But why don't we observe quantum effects in our daily lives? How can a world governed by quantum mechanics at its most fundamental level give rise to the predictable, classical reality we experience? The answer involves a phenomenon that acts as a gatekeeper between the quantum and classical worlds, continuously collapsing the wave function of reality itself. This phenomenon is known as quantum decoherence, and it plays a crucial role in bridging the gap between the bizarre quantum realm and the familiar classical world we inhabit. Decoherence occurs when quantum systems interact with their environment, causing them to lose their quantum properties and behave in ways that align with classical physics. At its core, quantum decoherence is a process of information loss. When a quantum system interacts with its surroundings, the delicate superposition of states that characterizes quantum behavior becomes entangled with the environment. This entanglement effectively spreads the quantum information across a vast number of environmental particles, making it practically impossible to observe or measure the original quantum state. Imagine a quantum particle existing in a superposition of two states, like Schrödinger's famous cat that is both alive and dead simultaneously. As this particle interacts with air molecules, photons of light, or any other environmental factors, its quantum state becomes increasingly entangled with these external elements. The more interactions occur, the more the particle's quantum information is dispersed into the environment. This dispersion of information happens incredibly quickly for larger objects. A dust particle, for example, interacts with trillions of air molecules in a fraction of a second, causing its quantum state to decohere almost instantaneously. This rapid decoherence explains why we don't observe quantum superpositions in everyday objects. Their quantum nature is masked by continuous interactions with the environment. Decoherence also provides insight into the measurement problem in quantum mechanics. When we measure a quantum system, we're essentially forcing it to interact with a macroscopic apparatus. This interaction causes rapid decoherence, collapsing the quantum superposition into a single, definite state that we can observe. In this way, decoherence offers a potential explanation for the apparent collapse of the wave function during measurement. It also suggests that the classical world we experience is not fundamentally different from the quantum world, but rather emerges from it through a constant process of information loss and environmental interaction. Our perception of a stable, predictable reality may be the result of our inability to observe the underlying quantum fluctuations that are continuously smoothed out by decoherence. This would mean that the solid, definite properties we associate with objects may be more illusory than we realize. The chair you're sitting on, for example, may not have a fixed position in space, but rather a probability distribution that appears fixed due to constant environmental interactions. Moreover, decoherence raises intriguing questions about the nature of time and causality. In the quantum realm, time can behave in strange ways, with effects seemingly preceding causes. Decoherence may play a role in establishing the arrow of time we experience, as the continuous loss of quantum information creates an irreversible flow from past to future. But as we grapple with the complexities of quantum mechanics, a surprising connection has emerged between particle physics and ancient mathematics. The golden ratio, a number admired for its aesthetic properties, keeps appearing in quantum calculations. Is this just a coincidence, or have we stumbled upon a hidden order underlying the fabric of the universe? The search for elegant mathematical patterns in nature has been a driving force in scientific discovery for centuries. Now, this quest has led physicists to explore the potential connection between two seemingly unrelated concepts: the golden ratio and a complex 8-dimensional structure known as the E8 lattice. The golden ratio, approximately 1.618, has fascinated mathematicians, artists, and architects for millennia. It appears in unexpected places throughout nature, from the spiral of a nautilus shell to the arrangement of leaves on some plants, but its presence in the realm of quantum physics is particularly intriguing. Recent research has uncovered the golden ratio in quantum mechanical calculations, specifically in the magnetic resonance of spins in cobalt niobate crystals. The E8 lattice's connection to fundamental physics became apparent when researchers proposed it as a unified framework for particle physics. This theory suggests that all known particles and forces might be represented as points on the E8 lattice. Remarkably, the golden ratio appears within the structure of the E8 lattice. The E8 lattice theory proposes that the physical properties of particles might arise from the geometric relationships within this 8-dimensional structure. But just as the E8 lattice suggests that our reality may be rooted in deeper, hidden structures, quantum computing explores the very foundation of these concepts. Quantum computers leverage the strange properties of quantum mechanics to perform calculations that were previously thought impossible. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in multiple states simultaneously due to superposition. This ability to exist in multiple states allows quantum computers to process vast amounts of information in parallel, potentially solving complex problems exponentially faster than classical computers. The power of quantum computing lies in its ability to exploit quantum entanglement. Imagine a problem that requires checking every possible combination of a set of variables. A classical computer would need to check each combination one by one, a process that could take years or even centuries for complex problems. A quantum computer, however, could theoretically check all possible combinations simultaneously. In the realm of drug discovery, quantum computers could simulate complex molecular interactions, potentially accelerating the development of new medications and treatments. However, the development of practical quantum computers faces significant challenges. Quantum states are extremely fragile and susceptible to decoherence. Maintaining the delicate quantum states necessary for computation requires incredibly precise control and isolation from external disturbances. The integration of quantum technologies is crucial for the development of a viable quantum internet, which would rely on entangled photons for secure communication. Quantum mechanics reveals a universe far stranger than we ever imagined. The fabric of reality is woven from probability and uncertainty. From superposition to entanglement, time paradoxes to the observer effect, quantum phenomena reveal a reality that is dynamic, interconnected, and profoundly mysterious. These revelations force us to confront uncomfortable questions about the nature of consciousness, free will, and our place in the universe. The universe we perceive may be an emergent property of quantum interactions, with our observations actively shaping the reality around us.